to this online seminar. Ooh, okay. Yeah, so today I'm going to tell you about some work related to cosmological signatures of dark photons. And this work has been done in collaboration with a pretty big group of people. James Bolton from Nottingham, Andrea Caputo from Tel Aviv, Sid Mishra Sharma, who's now at MIT, Josh Ruderman at NYU, and Matteo Vial at CISA. And the results that I'll be presenting are based on these three papers with the following archive numbers. And so I'm very happy to entertain any questions at any time throughout the talk, so just feel free to go ahead and interrupt me whenever you feel like it. So let me just jump straight in. I hope I don't have to give the usual introduction of what dark matter is, because I think this audience probably doesn't need much convincing that the particle physics of dark matter is important to study. And so what I'm going to do instead is to jump straight into describing one of sort of the most attractive paradigms in which we think of dark matter physics, and that is what we call the dark sector. And so the dark sector is essentially this idea that all of the particles that we know and love, for example, the electron, the up quark, the down quark, all live in the standard model sector. And then there's another sector called the dark sector, which contains not just the dark matter, but it could contain many other particles as well, including its own forces and stuff like that. That's all happening inside the dark sector. Both of the sectors are mostly separate with their own interactions. But the two sectors could actually interact weakly through some kind of mediator, which possesses some kind of small mixing with a particle in the standard model. And so one particularly important realization of this is called the dark photon, where we introduce this mixing term between the standard model photon and the dark photon, given by this FF prime term, with a small mixing parameter called epsilon. And in general, of course, the dark photon could have a mass given by MA prime squared. And so this weak interaction or mixing between gamma and A prime is the thing that is responsible for any interactions between things in the standard model sector and things in the dark sector. Now, one reason why this is such an important setup to study is because if you think about how we can build interactions between very light new particles in the dark sector and the standard model, if that's what you're trying to do, there aren't actually that many ways to build such an interaction. And it turns out that the dark photon is one of just a handful of ways in which you could write down a renormalizable interaction between the dark sector and the standard model. Another thing that's very interesting about this model is that it's very simple. Throughout this talk, you will hear only about two parameters related to this model. One, of course, is the mixing, epsilon, and the other is the mass, MA prime. And so these two parameters essentially just give you all the information you need to know about this model. So in this talk, I'm going to focus on two very simple scenarios of a scenario where the dark sector contains the dark photon. The first scenario is just the dark photon just simply existing without any further assumptions on any particles in the dark sector. So we just have the dark photon and we assume that there are no other particles in the dark sector. Even this assumption, with no further assumptions, already leads to very interesting cosmological signatures that I will talk about in the first half of my talk. The second scenario is that the dark photon actually makes up all of dark matter. And this is actually a very attractive possibility that many authors have considered over the last few years. And it's a very viable way in which you could generate all of the dark matter and use something that's ultralight, something like 10 to the minus 15 eV or so to generate all of the dark matter. And like I said, this possibility has been studied very extensively, and it's an important scenario to test. And this scenario leads to additional and very distinct cosmological signatures that I will talk about toward the later part of my talk. Okay, so the two scenarios that I just set out, are fun to study, but there are many ways in which you could study the dark photon. And in the next part of my talk here, I'm just going to try to convince you that one of the key ways in which you could understand whether the dark photon exists or not comes from cosmology. And there's a very good reason, especially if you're thinking about ultralight dark photons, to look for cosmological probes. So let's think, first of all, about what generically, this mixing term does in terms of observables. Like, what should we observe in the lab, for example? So this mixing term here, this epsilon FF prime term that you add to the Lagrangian, what it does is that it changes the photon and the dark photon states, like it mixes them. And so the photon that we normally think of in the standard model, it turns out that it's only an interaction eigenstate where the photon, actually interacts with things like the electron, the up and the down. But it's not actually a propagation eigenstate because of this mixing term that you have introduced. You need to, re-diagonalize the Lagrangian to sort of pick out like canonical mass eigenstates in order to find what the correct propagation eigenstate is. And if that sounds confusing, I mean, maybe I didn't explain it very well, but the analogy that you should have in your mind is mixing in neutrinos, which is exactly analogous. So we know, for example, that if we produce an electron-type neutrino from some kind of interaction, some kind of weak interaction involving the electron, you get an electron-type neutrino that's produced. It is produced in a flavor interaction eigenstate. And then as it propagates, it actually oscillates from one flavor to another. So for example, it could go from nu E to nu mu. And this is a fine example of the fact that you can have interaction eigenstates that are not propagation eigenstates. And the exact same thing happens when you introduce a mixing between the photon and the dark photon. So one interesting thing you could do in terms of trying to observe the existence of the dark photon is you could have two radio frequency cavities that are separated by some kind of wall, which is opaque to any photons. And then what you do is in one of the cavities that we call the emitter cavity, we put in we put in a ton of radio frequency photons that are bouncing around the cavity. These photons are produced in a flavor eigenstate. And because that's not a propagation eigenstate, it can oscillate into an A prime through the wall because the dark photon doesn't interact with regular stuff. The dark photon interaction eigenstate doesn't interact with regular stuff. And then have it oscillate back into regular photons in a cavity beyond the wall that we call the receiver cavity. And so what you do is, you prepare another cavity on the other side of the wall, which is really quiet, and you try to look for signals of photons sort of jumping across the wall by oscillating into dark photons. Now, these kinds of experiments are called light shining through wall experiments, and there's actually one going on right now in Fermilab called Dark SRF, which exactly implements this setup that I just showed you earlier. And actually earlier this year, they reported some interesting results, some interesting constraints on the dark photon parameter space, which remember it only has two parameters. It has the mass and the mixing. And you can see here that these kinds of light shining through wall experiments are particularly good at a mass, dark photon mass of about 1 micro eV or so. But you'll see something interesting on all of these plots, which is that for dark SRF, for example, if you look at how the limits behave as you go to lower and lower masses, you can see that it generally exhibits some kind of weakening. So that's what I'm going to explain to you, like why can't we do this search for very light dark photons, say something like 10 to the minus 9 eV in the lab. And this is because, essentially, if you look at how the oscillation behaves, how the photon oscillates into the dark photon and back into the photon, there is a characteristic length over which such oscillation occurs maximally. And this characteristic length L here is given by the energy of the photon that you're trying to get to oscillate into A primes, divided by the mass of the A prime squared. And if we put in some characteristic numbers, for example, if we're doing this with radio frequency photons, so a gigahertz photon, and for a mass of MA prime of 10 to the minus 6 eV, we find that the length of the characteristic length of the oscillation is something like a meter, which is something that we can build in a lab, right? A meter length scale is very manageable for humans. But of course, if you think about lighter and lighter dark photons, for example, if you go to 10 to the minus 9 eV dark photons and you plug in all the numbers again, and you look at what the characteristic length is, you get something that's 10 to the 6 meters, which is starting to be comparable to the size of the Earth. And so these kinds of experiments are much harder to do terrestrially. But of course, once you start thinking about such long length scales, your mind should be, thinking about astrophysical or cosmological probes. And so this is the first reason why light dark photons, especially things like 10 to the minus 9 eV and below, are best probed by cosmology and not by terrestrial probes. The other thing I would say is that when you're in outer space and you have photons traveling through the universe, right? We know that the baryons in the universe are slightly ionized, and so they form a very sort of weak and very sparse plasma. And this ends up giving us very interesting propagation medium effects that I will now describe in detail that really can help us get conversions between photons and dark photons and makes cosmology sort of a very beneficial way in which to look for such conversions. Okay. And so the next part of the talk, I'm going to discuss, how dark photons and photons oscillate into each other in the presence of some of these in medium effects. So the rough picture that I've given you so far when I talked about dark SRF, for example, is what we call a non-resonant oscillation, where you have oscillations between photons and dark photons happening in a vacuum. And in this case, the way in which oscillations behave looks very similar to neutrinos, as I said. And it's sort of a continuous process where the photon oscillates into dark photons and vice versa. So it's sort of like a sinusoidal kind of probability of oscillation. But like I said, if you look at what's happening when photons travel to us in outer space, it travels through a very weak plasma. And if we put in if we ask what is the plasma frequency, or equivalently for the purposes of this talk, what is the effective plasma mass of photons in the gas in outer space? If we put in some characteristic numbers, like for example, if we put the mean electron number density today, n sub e, which is roughly 2.5 times 10 to the minus 7 per cm cube, we end up with a plasma mass of something like 2 times 10 to the minus 14 eV. So this is an effective mass in some ways that a photon has in the plasma in outer space. And so you might start to see some interesting effects once you have, for example, your dark photon mass being very close to the plasma mass. And this is indeed what happens. And so if we look at a plot of the homogeneous plasma mass, so if we assume that the universe is completely homogeneous, just taking the average number density of electrons, we can also plot, what is the homogeneous plasma mass as a function of redshift. And here I'm showing you that a plasma mass varies from something like 10 to the minus 9 eV at a redshift of 1,000, which is when recombination occurs, all the way down to 10 to the minus 14 eV today. This is done, just by plugging in the numbers for free electron fraction and the mean electron number density to get today. So after recombination, the plasma mass varies by 5 orders of magnitude between 10 to the minus 14 and 10 to the minus 9 eV. And if you look at the shape of the evolution of these of the plasma mass, you can see some interesting features as a function of redshift, and this just corresponds to recombination when the universe transitioned from fully ionized to mostly neutral, as well as reionization when the universe transitioned again from mostly neutral to fully ionized due to the fact that stars were emitting UV radiation, which is why you see these features when you look at the plot of plasma mass as a function of redshift. Okay, so the key numbers to keep in mind here are 10 to the minus 14 to 10 to the minus 9 eV in terms of the plasma mass. And so what happens when you have, for example, a photon traveling through a medium where the plasma mass is sort of scanning between the values of 10 to the minus 9 eV all the way down to 10 to the minus 14 eV, right? Suppose, MA prime is sort of in the middle of this range, so something like 10 to the minus 13 or 10 to the minus 12 eV. Initially, when a photon comes from, let's say, the cosmic microwave background, right? It's traveling from far away. It travels through the plasma, and it starts off with a effective plasma mass, which is much greater than MA prime. And the right way to think about how the photon and the dark photon sort of interacts with each other is to think of this as some kind of quantum two-state system, right? Where you have one state which looks very much like the photon and one state that looks very much like the dark photon. And so they initially are separated in energy, right? The photon has an energy given by the plasma mass m gamma, and the A prime has energy given by the A prime mass, which is ma prime. And initially they could have very large separations in terms of the energy. And another way to think about this is that you can write down a Hamiltonian governing this two-state system, where initially when at very high redshifts, when a photon has a very high plasma mass as compared to the A prime mass, you have a Hamiltonian that is more or less diagonal. So the two states don't mix with each other very much. And then at some point, as the universe expands, m gamma decreases as a function of redshift. You come to a point where m gamma is going to be equal to m prime. And at that point, the two states, the two quantum states become degenerate. And if you look at the Hamiltonian, you'll find that actually at this point, the off-diagonal terms in the Hamiltonian will dominate over the diagonal terms. And in this case, what happens is that you get maximal mixing between the two states. And so at this point, if you started off initially with a photon, some of the photon will now oscillate into a dark photon at this point due to the resonant condition of m gamma equal ma prime being met. And then, of course, at late times, what happens is that the two energy levels split again, and they end up becoming, again, separate states. But by this time, some of the photons would have already converted to A primes at the point when the resonant condition is met. And so you can actually, this is actually a simple sort of two-level system, quantum mechanics, with some time-varying energy level, time-varying energy levels. And you can actually solve this two-level system and figure out what is the probability of conversion between, for example, starting off in the photon and then transitioning to an A prime state at late times. And the answer just looks something like this. It's proportional to the mixing squared, which is something that we would expect. It's proportional to the mixing squared. It's proportional to this vacuum the inverse of the vacuum oscillation length that I told you about earlier on, which was omega over ma prime squared. And then it's proportional to how slowly the two states kind of passed each other at the resonant condition. If the two states sort of stayed at the same energy levels for a long period of time, then the probability of conversion between one state and the other goes up. Now, if you compare this with what we had for the vacuum oscillation probability, which scales as something like epsilon squared times sine of this number, and if we make the approximation that L is very, very small, then what happens is that the probability scales as epsilon squared, which is the mixing squared as expected, times the characteristic oscillation, 1 over the characteristic oscillation length, times the length over which you allow the oscillation to occur, which for terrestrial experiments is something like a few meters, or maybe at most a kilometer or something. But if you compare that with what you get for the resonant case, when you have this m gamma equals ma prime condition being met, the length scale that appears in the probability is this time at which the two states sort of stay at the same energy level, which if you think about it, like cosmologically, these two states are sort of evolving according to the expansion of the universe. And so the time scale that governs how slowly the two states sort of pass each other is the Hubble parameter. And if you compare the Hubble parameter to any length scale that you can get terrestrially, obviously the Hubble parameter is going to be much larger. And this is why these kinds of resonant oscillation, where you have m gamma equals ma prime, where this condition of m gamma equals ma prime being met, leads to very strong conversions between photons and dark photon. And this is one of the key reasons why cosmology is very important in terms of looking for effects in a mass range of something like 10 to the minus 14 to 10 to the minus 9 EV. Okay, so at this point, let me just remind you of the key takeaways of why cosmology is important in terms of looking for ultralight dark photons in particular. The first takeaway that you should have is that because cosmological scales are so massive, they're really good for looking at anything that takes a long oscillation length, which is something that happens when the A prime mass is very light. So something like less than 10 to the minus 9 eV is already corresponding to astrophysical scales usually. Another thing to take note is that there are resonant conversions between photons and dark photons that occur when the effective plasma mass, m gamma, is equal to the mass of the A prime, ma prime. And at this point, you get a strong conversion between the two states that scales as the size of the observable universe. And this leads to very strong conversions. And this makes cosmology a very effective probe of dark photons. So before I move on, are there any questions about resonant conversions at this point that I can answer? All right, so if not, then let me discuss what happens when you have resonant oscillations, conversions between photons and dark photons occurring in the real universe. And this, is based on some of the papers that I showed you earlier on that we wrote in 2020, but also the same set of ideas are sort of being studied at roughly the same time by a few other groups. And so I encourage you also to look at these other papers that I show here. So now that I've told you, like photons convert to dark photons through this resonant conversion process, you should be asking, what kinds of signatures should we expect to get? So one thing that we would like to have is that we would want to have some source of photons coming to us from really far away, and we want these photons to undergo some kind of resonant conversion into dark photons. And the good thing for us is that we know that we have such a source of photons, the cosmic microwave background, and we actually know exactly what the spectral shape should be, which is that it should be very close to a perfect black body. And indeed, when the FIRES experiment was active in the 90s, and we took a spectral measurement of what the cosmic microwave background is, this is what they got on the left in the top plot. You can see the intensity of the cosmic microwave background is a function of frequency. There are data points on this plot. It's just that the error bars are so small that you can't see the error bars. They're hidden behind the fit, which is a fit to a black body distribution with a CMB temperature of 2.725 Kelvin. And so if I subtract off the black body fit to give you the residual, you get what is shown in the red data points at the bottom. And you can see that if you compare the residual with the actual intensity values, you can see that we've measured the spectrum of the CMB to something like 1 in 10 to the 4 precision, which is a really one of the most precise things we can measure, especially in astrophysics. You can see the data points are shown in red, and they're consistent with the fact that the data points do follow a black body distribution. And now if you introduce a dark photon, for example, with this mass here that I'm showing and this mixing parameter, then what's going to happen is that if it is possible for photons to resonantly convert into dark photons, then some of these photons that are traveling to us from afar are going to disappear. And this is going to end up distorting the black body that you see. So for example, if you have these parameters that I'm showing here, the spectrum that you should get should follow the blue dotted line that I'm showing here, which you can see shows a strong deviation from the black body, especially at low frequencies. And you can see that these kinds of dark photon parameters are clearly disfavored by the data coming from FIRES. And so this is the idea. We're going to look for distortions to the CMB coming from photon to dark photon disappearances. And so if we think about, again, the resonant conversions that I told you about, if we assume once again that the universe is completely homogeneous, then everywhere in the universe you have the same value for m gamma. And so if you fix some value of ma prime, so for example, an ma prime of 10 to the minus 12, then if we assume everything is homogeneous again, then what happens is that when the plasma mass crosses the dark photon mass, for example, at this point here, which happens at maybe a redshift of about 200, the point being where the red line crosses the black line, which happens at a z of about 200, you're going to get resonant conversions between the two, and some of the photons are going to disappear. And so because the dark photon mass, because the plasma mass scans values between 10 to the minus 14 to 10 to the minus 9 eV, any dark photon mass between these two masses will lead to some kind of resonant conversion, sometimes even multiple resonant conversions. And because of that, you're going to see some disappearances in the CMB that you can hopefully constrain, as a function of epsilon and MA prime. Now, the previous plot that I showed you, assumed that the universe was completely homogeneous, which of course is a very poor assumption. Really what happens is that every CMB photon that comes to us from the surface of last scattering travels through a universe that is very inhomogeneous. So it's going to pass through patches of different densities and also therefore patches of different plasma masses. And each photon is going to see a path that's going to be different from every other photon around it. So for example, here is an example of a box that we have generated with realistic fluctuations in the plasma mass shown here. You have overdensities in the plasma mass shown in red and underdensities shown in blue. And you should imagine a photon kind of traveling through this box and then having some kind of, resonant conversion along the way. And so if you plot, for example, the plasma mass that the photon experiences as a function of redshift as it goes through this box, you can see in this red wiggly line here that, of course, as it passes through all of these different patches, the plasma mass is gonna vary a lot, right? I mean, significantly. And so you see all these little wiggles. And of course, every time the plasma mass matches the A prime mass, you're going to get some resonant conversion. So every time this wiggly red line here passes this gray line here, where we take the A prime mass to be something like 2 × 10⁻13 eV, you're going to get some resonant conversions. And you can see that there are lots of resonant conversions happening between a redshift of something like 106 all the way down to 94. And so you might think this is intractable because each photon is going to do something different. So how are you going to determine like what is the mean result averaging over all of the photon path? But surprisingly enough, you can actually write down an analytic formalism that allows you to average over all possible photon paths as they travel from the surface of last scattering all the way to us. So here I'm showing you at the bottom the differential probability of conversion from photons to dark photons as a function of redshift. And you can see here I've drawn a red line every time there is a crossing between the plasma mass and dark photon mass, where we would expect some amount of resonant conversion. And you can see like every time we draw a line, that's where we see some conversions, and that there are a lot of conversions happening when the mean plasma mass, if we average over all of space, is equal to MA prime, which happens in this case at a redshift of about 100. And then it sort of goes away once the mean plasma mass drops below MA prime significantly at a redshift of something like 90. And in blue, this is the analytic result that we computed. And you can see here that the differential probability quite closely mimics, how closely spaced the lines are. So when there are no lines or when they're very spaced apart, quite far apart, you can see that the probability is low. And then where they're all sort of clumped together, the probability is high. Now, usually I won't show you like all the math that goes into this, but it's really interesting and it's sort of simple enough for you to understand how it's possible to get some kind of analytic formalism. So if we look at the form in which we obtain, the form of the probability of conversion from photons to A primes, it looks something like this, right? The mixing squared times this inverse of the oscillation length times this particular, time scale here given by how quickly how quickly the photon mass passes through the dark photon mass. And this we have to evaluate every time we get some kind of resonance along the path. And if you think about it, you can actually easily write this sum over all of the different resonant conversions as some kind of integral over some delta function, where the delta function enforces the resonant condition where m gamma squared must be equal to MA prime squared. And then, of course, the sort of the contribution to the probability again scales as epsilon squared times MA prime squared over omega. Now, the thing that you want to do is you want to average over all possible photon paths, which means that if you think about it, at every point in time, if you draw a sphere around us from some distance away from us, what we want to do is we want to integrate over the probability distribution function of m gamma squared in that shell. And so all we're doing here is, in order to average over the sky, what we want to do is we want to insert this integral over the probability density function of m gamma squared as a function of t, and do this integral over all possible values of m gamma squared. But because you have a nice delta function here in the expression, you can very easily complete the integral to get the expression that you would need to evaluate the sky average probability of conversion. And this is just given by integrating over some line of sight times, the coupling squared times some mass parameters, frequencies, and then multiplied by the PDF, the probability density function of finding a value of m gamma squared that is equal to m prime squared, where the resonant condition can be met at each function of time. And so this is a very particularly simple expression. And if you didn't follow the whole argument about how we got this expression, all you need to know is that the sky averaged probability of conversion from photons to dark photons, including all the effects of inhomogeneity, just comes down to knowing what the probability density function is of the plasma mass squared as a function of time. Okay, so that's the key takeaway of this part. And so now we can ask, what is this PDF? What is this PDF of m gamma squared? Like I said, m gamma scales as something like ne to the half, and so m gamma squared is proportional to the number density of electrons. And sweeping some complications under the rug, this number density of electrons just scales essentially as the number density of baryons. And so essentially, the PDF of finding m gamma squared as a function of time is just ultimately just proportional to the PDF of finding some baryon over density as a function of time. And so what we've done is we've reduced the calculation of this conversion of photons to dark photon, taking this sky average probability of conversion to requiring just this one cosmological parameter, which is the PDF of baryon fluctuations. And this is something that we understand pretty well in cosmology. So for example, in the linear regime where all of the fluctuations are very small, we know that the baryon over densities simply track, are essentially governed by a Gaussian probability density function given by some variance sigma b squared that we can extract from the power spectrum of matter fluctuations, which is something that we can compute very easily in cosmology. And so when you look at redshifts above 20, for example, when fluctuations are very small and Gaussian, we have the complete PDF, and so we can compute the mean probability of conversion between photons and dark photons. And so in order to test this analytic result that I told you about earlier, what we did in our paper was to also make sure that this analytic result compares well with simulation. And so what we did was we simulated a box where you have fluctuations happening in the linear regime where everything is Gaussian. And we took lines in this simulation and sort of calculated the mean probability of conversion between photons and dark photons across many different lines in this box. And the result that we get is shown in the dashed line on the right. As a function of z, we plot the differential probability of conversion. And here, I've overlaid the analytic result, which is shown in the solid red line. And you can see that the agreement is very, very good, which shows that the analytic argument that I gave you earlier does indeed work when compared to simulations. And so with this, the key takeaway is that we're able to capture, perform a sky average of photon to dark photon conversions, accounting for the fact that the universe is completely inhomogeneous by finding this nice analytic method. The last thing I would say about this analytic method is to make some comments about the nonlinear regime, which is complicated. But the punchline is that in a nonlinear regime, the probability density function of baryon fluctuations is no longer Gaussian. And so we have to figure out a way to kind of model what the PDF is. And we don't actually know what the PDF of baryons is at this time. And so what we did was we adopted sort of two very different ways in which we could characterize this PDF. So one was just using, just assuming that a PDF follows a log normal distribution, which is something that's done very often in the literature. For, if you want to do a phenomenological study of the baryon PDF, this is something that many people have done. And then fit the variance of this log normal distribution using simulation data. Another thing that we did was to sort of get some PDFs that people have computed for dark matter analytically. In this paper here, written by Ivanov and co, where they actually write down what the PDF is expected to be for dark matter. And we take that and assume that the baryon distribution is similar to the dark matter and use that to compute the probability of conversion. And so here on the left, I'm showing you the various PDFs that we actually adopted. Without going into too much detail, you should look at the red and the blue lines, which are the two main methods that we use. And you can see here that, if we are looking at parts of the PDFs where we're looking at very significant overdensities, where you have like overdensities on the order of like 10 to the 2 or 10 to the 3, or very underdense regions where it's like 10 to the minus 3, for example, then these two PDFs disagree a lot. But in sort of near the mean, and up and down to something like 10 to the minus 2 to 10 to the 2 underdensities and overdensities, the two methods kind of agree pretty well. And so what we did was we only included conversions in overdensities and underdensities between 10 to the minus 2 to 10 to the 2, just to be conservative, and use that to kind of set constraints on photon to dark photon conversions. Okay. Are there any questions at this point regarding the methods that I've just described? Okay, if not, let me just jump straight into the result. Let me remind you again what we're looking for. We are looking for disappearances of CMB photons due to resonant conversions. And we're going to use the analytic formula that I just described to take a sky average of the disappearance probability and then compare the averaged disappearance and the spectrum that results from such a disappearance with the virus data points that you see here on the left. Now, if we do this, this is the result that we get in terms of the two parameters that are important in the dark photon model. That is the mass of the A primes and the mixing parameter epsilon. And our result here is shown in the shaded region. And the red and the blue lines are related to the choice of the PDF modeling that I just told you about. But like I said, the differences between how we model the PDF is very slight. So essentially, there's just one result here, which is the shaded region. Now, the interesting thing is to compare this result with what you would have gotten if you assumed that everything was homogeneous, which is shown in the dotted line. You can see that, at very high MA prime, most of the resonant conversions happen during a time when the universe was very homogeneous anyway. And so the two limits agree at high MA prime. But then once you come down to something like 10 to the minus 12 EV or so, you find that you can get conversions happening in overdensities during reionization that you would have missed if you assumed that the universe was completely homogeneous. And this strengthens the limits significantly at a mass of 10 to the minus 12 EV. Furthermore, at a mass of 10 to the minus 15 EV, which is very light, if you had assumed that the universe was homogeneous, you would have said, well, the CMB photons never undergo any resonant conversion. But of course, the universe has pockets where you have fluctuations of density downwards, so that you have regions which are very underdense. And this allows very light dark photons, this allows CMB photons to resonantly convert into very light dark photons. And so this extends the limits down to smaller masses, down to almost 10 to the minus 15 eV or so. And also you see that, actually assuming that everything is homogeneous is not a conservative assumption, in the sense that when you do the correct calculation with inhomogeneity, you find that the limits can actually weaken. And the way to think about it is that if you assume that everything's homogeneous, all of the conversions happen at one redshift and at one particular point in time. But if there are fluctuations, then what happens is that the conversions actually kind of spread out over time. And so inhomogeneities can actually push some of the probability of conversion into the future. And this leads to a weakening of the constraints. And so if you're looking for constraints on dark photons, the existence of dark photons between a mass range of 10 to the minus 15 to 10 to the minus 9, please make sure to look up our results, which update the previous result. And this is done in the February 2020 paper that I've shown up here at the top of this slide. Okay, so the punchline for this part of the talk is that if you have dark photons and they simply exist and you don't make any further assumptions about the dark sector, then these dark photons can be probed by cosmology. And it's very easy to include the fact that the universe is inhomogeneous into these constraints. Okay. Again, I'm going to pause for questions. Were there any questions about this part of the talk? Okay. So if not, I'm going to talk about the second scenario that I discussed earlier, which is dark photon, dark matter. So let me remind you again, the second scenario is that there is a dark sector, but the entire dark sector is made up only of A primes or dark photons. And typically we're looking for ultralight dark matter, which is something in the range of 10 to the minus 14 EV to 10 to the minus 9 EV again. And like I said, if you look at dark photon, dark matter, you're going to get additional and distinct cosmological signatures to the ones that I've just discussed in the previous example. So in particular, all of the resonant conversion stuff that I told you about, where we were looking at photons oscillating into resonantly converting into dark photons and causing CMB photons to disappear, also apply for dark photon, dark matter, resonantly converting into visible photons. So the conversions kind of go both ways, gamma to A prime as well as A prime to gamma. And you get resonant conversions every time the dark photon mass, M A prime, is going to be equal to the plasma mass, M gamma. So in the case of A prime dark matter, these conversions end up giving you very low frequency photons. And so, for example, if your A prime mass is something like 10 to the minus 14 EV, it's going to be a frequency of something like 2.5 hertz, which is way, way, way lower than radio frequency. And if you ask what happens to these photons when they are emitted, well, they're actually absorbed very rapidly in a process called free absorption. And so the picture that you should have in mind is, before resonant conversion, you have a bunch of dark matter particles, dark photon, dark matter particles in purple, kind of sitting around in a baryon gas that has some free electrons that gives it some plasma mass. And then when the plasma mass is equal to Ma prime, some resonant conversion occurs. And so some of the A primes convert into photons. These photons get absorbed very rapidly, almost instantaneously, by all of the free electrons that are nearby. And this causes these free electrons to heat up. And this process, free absorption, you should think of as just the inverse of Bremsstrahlung. And so can we detect this effect? Can we detect the heating that comes from this absorption? And the answer is yes. So what happens is, you're gonna heat the intergalactic medium, and you're gonna raise the temperature of the gas. And we know roughly from Lyman-alpha forest data, between a redshift of 2 and 5, we know that the intergalactic medium has a temperature that does not exceed 10 to the 4 Kelvin. And so if you have this absorption of photons that heats the gas past 10 to the 4 kelvins in your model, then you can set some constraints based on the Lyman-alpha forest data. And so again, on the left here, I'm showing you a plot of Ma prime against epsilon, assuming that we have dark photons making up all of the dark matter. And you can see that for even, an epsilon as small as 10 to the minus 13, you get too much conversion of dark matter into these low frequency photons, which leads to too much heating, and you're ruled out by the Lyman-alpha data. And so if you include inhomogeneities as well, using the same formalism that I talked about, you get the result that we show on the left here in blue and in red. Again, they're roughly the same. And you can rule out very strongly a wide range of parameter space for ultralight dark photon. Now, let's take a closer look at what the redshift, the Lyman-alpha data actually says. So let me just remind you briefly how the Lyman-alpha forest works. So what happens is you have some quasar that is very far away, so something that's emitting UV radiation at very high redshifts. As the emitted spectrum travels from the source to us, the spectrum redshifts, and then it passes through different regions where you have pockets of neutral hydrogen. And what neutral hydrogen does is that it absorbs UV radiation very efficiently, because there are all these hydrogen energy levels that can absorb a photon, causing the hydrogen atom to excite. And so as a result, when the spectrum arrives at us at our location, we see a bunch of troughs corresponding to neutral hydrogen gas absorbing UV photons at a particular point in the line of sight between us and the quasar. And based on the statistics of these lines, so for example, how many lines do you see, or how broad these lines are, we can say some things about the state of the intergalactic medium at a redshift of between, for example, 0 to 5. So on the right, I'm showing you some data that we have had for many years now. And so the data points that you see here are data points coming from the Hubble Space Telescope, data points coming from something called the Cosmic Origin Spectrograph that is on the HST. And this data comes from looking at Lyman-alpha forest measurements coming from sources that are very near to us, so very, very late time, at a redshift of 0.1 or so. And the data points correspond to the probability distribution of these absorption troughs, the widths of these absorption troughs. So on the x-axis is essentially the widths of these troughs, and on the y-axis the probability of finding such widths. And so the data points correspond to what you see at low redshifts, and the lines are models that come from simulations that have been calibrated based on Lyman-alpha data at high redshifts, so at a redshift between 2 and 5. And what you see here is that the simulations that have been calibrated to high redshift data tend to want to prefer a distribution that is peaked at lower widths, whereas the actual observations coming from Hubble Space Telescope and the Cosmic Origin Spectrograph want a distribution that prefers higher widths. And so this disagreement has been known for something like 6 or 7 years, and suggests that when you calibrate, when you do a simulation calibrated to high redshift data, it kind of underpredicts what the temperature of the gas is at late times. It wants a colder intergalactic medium than what is actually measured by the Cosmic Origin Spectrograph. And this is interesting. And you can try to play various games to try to explain this astrophysically, but it turns out that it's really hard to get this additional heating between a redshift of 2 and a redshift of 0, which is where the heating is expected to kick in, right? So one thing you can try is, for example, you can say, let's try to increase the amount of feedback, so the amount of sources that are emitting UV radiation to try to heat up the gas even more between a redshift of 2 and 0, so that we can get agreement between simulation and the data. But the unfortunate thing is that generally, if you try to increase the amount of radiation that you're emitting, you also increase the ionization levels, and so you have fewer pockets of these like neutral hydrogen gas to do the absorption. And as a result, you can see that no matter how we change the feedback on the left, so if we look at all the different lines that are on the plot, you don't really get a distribution that shifts to the right to get better agreement with the data. Another thing you could do is you could say that each of these sources that are emitting a harder radiation spectrum. So they're emitting more UV photons that then leads to more heating. But again, the kinds of spectrum, the spectrum that you need in order to accomplish this extra heating is shown in blue on the right. So in blue, on the x-axis, energy, and on the right is on the y-axis, it's the spectrum of photons, UV photons emitted by these sources. You need a spectrum that looks something like what is shown in blue to achieve the additional heating. And if you notice, the spectrum in blue is sort of rising without end to very high energies of like 100 eV and above, which is sort of very unexpected and very almost unphysical. And so we don't really have a good explanation in terms of astrophysics for the heating discrepancy between what we expect at high redshifts versus what we actually observe at low redshifts. So let me tell you what the discrepancy is in terms of heating. It turns out that the discrepancy is something like 6.9 eV per baryon of heating that is missing between a redshift of 2 and 0, which is a lot. Like that is 6.9 eV is very much comparable, even greater than the energy that's available to baryons, the typical energy that's available to baryons in the IGM at a redshift of 2. And so it's a lot of heating that's missing. And it also was a funny density dependent. So you need the heating rate to have some dependence on the density of baryons in the region. And this density dependence that you see here, which is density to the 0.6, is actually a really funny number, and it's really difficult to kind of reproduce this effect. There have been some possibilities that people have talked about, including the fact that we're not simulating turbulence in the intergalactic medium well enough, or maybe some additional contribution from dust. But neither of these explanations are concrete or really that convincing at this point, but they are a possibility. So one thing that we could do, based on all of the dark photon, dark matter heating that I just told you about, is to just try to see if dark photon, dark matter could explain the discrepancy between what we see at a redshift of 2 to 5 versus what we see at a redshift of 0. And so what happens is, you introduce some heating that comes from these conversions. And if you look at the plots on the top, on the left, I'm plotting, the temperature of the gas as a function of redshift. The top left panel corresponds to a fixed dark photon mass and a change in the mixing parameter. And of course, what happens is that just changes, how much heating you actually dump into the gas based on this resonant conversion. And another thing you can do is, instead of adjusting the mixing, you can adjust the mass. And what that controls is it controls when the conversion kind of happened. And so you can sort of push the conversions to be later or earlier. And so what we find is that if you have a dark photon mass of something like 8 × 10 to the minus 14 EV, accounting for all of dark matter, then you will get some conversions, resonant conversions into these, photons that are then absorbed, leading to heating, and you can get sufficient amounts of heating to bring the two data sets to be consistent with each other. And also you get a nice density dependence of delta to the half, which is very close to the delta to the 0.6 dependence that we needed in order to explain the data properly. And so if we do a fit to all of the dark photon parameters in terms of mass and the kinetic mixing parameter, we find that we get very good agreement for a mass of something like 8 × 10 to the minus 14 EV with a mixing parameter of a few times 10 to the minus 15. And if you compare the probability density function of the trough, the absorption widths of the troughs, with no dark photons, I don't know if you can see it properly, but it's shown here in gray, and that's a very bad fit to the data, and that's the same bad fit that you saw in the earlier slides. And introducing dark photons, you get the lines shown in either blue or red, and you can see here that it has successfully shifted the PDF to higher widths, and in fact gives a very good fit to all of the data points, and it reduces something like I think something like 3 or 4 sigma tension down to 1 sigma. And so that's I would say it's a tantalizing hint that dark photon dark matter might be doing something interesting, but obviously this is very far from being conclusive. One thing I would say is that because of the way the resonant conversion works, if you think about how the resonant conversion works, resonant conversions happen in underdense regions before it happens in overdense regions. And so one thing that we could look for is we could look for signs that, at high redshift, that underdense regions are actually hotter than overdense regions. And this is something called the inverted temperature density relation. And it seems that there is some evidence for such an inverted, for such a relation at these redshifts. But this is something that we want to investigate further. And we want to make sure that this inverted temperature density relation is consistent with the dark photon dark matter picture that I just presented earlier. Even if this dark photon dark matter thing isn't real, one thing we could do is we could take all of the simulations that we have done where we have included these dark photon dark matter models and evaluated what the temperature looks like as a function of time. We could take these simulations and set very robust limits on dark photon dark matter. Previously, the previous constraint that I showed you was done very approximately by saying, well, we know that the temperature between redshift of 2 and 5 cannot exceed 10 to the 4 kelvins, which is a very sort of hand-wavy way of doing things. But now we can actually do it accurately with the help of these simulations. And this is something that we want to work on going forward. And so that's something that I think I hope you will stay tuned for, and we hope to release some interesting results on either or both of these topics later on in the year. And so that just brings me to the last slide of my talk, which is just a very quick summary of what I've said, which is that if you're thinking about dark photons, especially ultralight dark photons, you should be thinking of the CMB as an excellent probe of photons disappearing into dark photons. And in the opposite direction, if you're thinking about dark photon dark matter, you should be thinking about signatures where you have these dark photon dark matter candidates resonantly converting into photons, which then leads to a heating of the gas. And this can potentially be detectable, or maybe it's been potentially detected in Lyman-alpha forest data. And please stay tuned for future results later this year. That brings me to the end of my talk. Thank you so much once again for inviting me, and please let me know if you have any questions. Thank you.
Yeah, thank you. Thank you for this nice talk. So is there any question from the audience? You can unmute yourself.
Hello, can you hear me?
Hi, yes.
Yes, yes.
Yeah, I'm Li Gong. I have one question on the CMB constraints on the dark photon dark matter. I mean, if there are some comparisons, for example, if there could be some other dark matters like the dark matter, what would be the difference for the CMB constraints?
Sorry, could you say that again? So you're talking about dark photon dark matter constraints, right?
Yeah, I mean from a CMB. Yeah, from a CMB. CMB distortion.
Yeah, so for CMB, the example I showed you was photon disappearing into dark photons.
Yeah.
Yeah. So this one has no assumption being made on A primes being the dark matter whatsoever. Like A primes just have to exist; they don't have to be the dark matter.
Okay, if there are some other light particle can induce some inhomogeneity in the CMB.
Like what other light particles are you thinking about?
Such as some other G prime, for example.
Oh, so you're talking about like if you have two A primes. You have two different dark photons. Is that what you're asking?
If there are some other people consider this is bosonic dark matter, if there are some other, for example, fermionic dark matter.
So first of all, I mean, I just want to reiterate again, like these constraints the ones that I'm showing you here based on a CMB that we worked out do not depend on the A prime being the dark matter. So A prime is not the dark matter in this case. So, the only requirement that we set to get these results is that the A prime exists, and then there's nothing else in the dark sector. So it's actually got nothing to do with dark matter at all. Of course, if you have multiple, if you have multiple A, you have an A prime, you have a Z prime, or like you have like other things that mix with a photon, then of course you will get multiple conversions, and you'll get a 3-state system, which in some specially tuned cases I can see that it might be a little bit more complicated. But I think if you have 2 other candidates which are sort of well separated, then it would probably reduce just to like having 2 different things to convert into. Did I answer your question, or were you asking something else?
Almost. Okay. Thank you.
Okay. Thanks.
Yeah, is there any other questions?
So may I ask one question?
Please.
Thanks for a nice talk. So I have a question about the epsilon, the notation here. So in your model, in this model, I think you mentioned this epsilon as a 3 parameter, right? But in some case, people can consider some loop contribution to generate the size of this epsilon. And in your study, your epsilon is so small. So I wonder if you have one UV model, how can get this epsilon so small?
Yeah, so there was a very nice paper by a bunch of people at Minnesota, including Maxim Pospelov, where they sort of investigated all of the different ways in which you could generate epsilon. Of course, like you're right, like the generic sort of loop diagram that you would write down with order 1 couplings, right? You would get an epsilon that is 10 to minus 1, 10 to minus 2. But for example, one simple thing that you could do is if you have cancellations in the loop, then you're suppressed by something like log of like the 2 masses. That's one way in which you could bring the couplings down. You could also introduce additional symmetries to ensure that the loop contribution that gives you the epsilon occurs, at 2 loops or 3 loops. And that's quite easy to arrange. One way in which you could do it is if it was only mediated by graviton, which is a possibility, and that can give you very small epsilon. And so actually small epsilons are not that difficult to arrange if you set up the symmetries correctly and push the contributions to 2 loops or 3 loops. I can sorry, who asked me that question? I can send you the paper which goes through all the different possibilities. Yeah.
Okay, I asked this question. So
okay, hi. Okay, great. Yeah.
Reference. Thank you.
Yeah.
Yeah, is there any other questions? Yeah, I have a naive one. I haven't worked on this dark photon things. So I'm wondering, considering this conversion from the photon to dark photon, is there any other constraint other than the CMB in the parameter range you consider here?
Yes. So dark SRF, yeah. So dark SRF, and so let me show you a better plot. So dark SRF is this orange line here, and this is the projection. So they've just started their first run. I'm not sure what, I think this is the eventual like full run, what they expect. And so you can see that, in parts of this parameter space, they're actually going to do much better than cosmology. Of course, between 10 to the minus 15 and 10 to the minus 12, cosmology is still much better. But dark SRF is going to do a pretty good job. The other thing that is that people have studied is the magnetic field of Jupiter. And remember in my talk, I said that, you know, once you go to like 10 to the minus 9, then you start thinking about like Earth, sort of Earth size. And if you go up to 10 to the minus 14 eV, you're thinking about like Jupiter size. And so the existence of the dark photon actually, you know, kind of distorts the magnetic field that is around Jupiter. So the naive way to think about it is that you expect the magnetic field to be roughly a dipole around Jupiter, but the existence of an A prime that has 10 to the minus 14 eV, which has a Compton wavelength the size of Jupiter, would make it not a dipole. And people have tried to set constraints this way. I've always been very skeptical about how well you can actually model the magnetic field of Jupiter to get such results, but people have claimed such constraints, and you can see here we've put them up here. So very weak, but you know it extends to past our 10 to the minus 15 mark, and so it's actually the strongest bound if you look at 10 to the minus 15 eV.
Okay, is there any other constraint like in this measurement, like from like supernova or something like that, the stars from the stars?
Good, yeah, good. So one thing that you always have to keep in mind, and this is a mistake that we have seen many times in the literature, is that anytime you have a dark photon, the interaction between the dark photon and the standard model is always suppressed by epsilon, not just by epsilon, but epsilon times ma prime squared. And so if you're in a supernova, for example, anytime you produce a dark photon, your processes are sort of at the MeV scale. And so all of those production cross sections are suppressed by epsilon ma prime squared over MeV squared. And so the production rate of very light dark photons is actually very small in supernovae and so on, which is why you don't see any like other astrophysical constraints in here. And it's the same reason why the dark SRF constraints are sort of have this like not so favorable power law going up. Yeah, so it's actually really difficult to constrain in this region. We have some interesting ideas also to do maybe with the CMB power spectrum, but we're still thinking about that, and I don't want to say any more until we get good results. Yeah.
Okay, thank you.
Mm-hmm.
Is there any questions? You can also type in the chat. Okay, if no more questions, let's thank our speakers again, and yeah, thank you for this nice talk, and I hope you can visit us in the future at some time.
Oh, I would like to. Yeah, that'd be great.
Yeah, good. Okay. Yeah, and could you send your slides to us, and so we can post it together with this video on our website? Good.
Yeah,
Thank you.
good. Yeah. Okay.